In this video, I'd like to talk about some necessary conditions for residuals in order to have a valid statistical inference. So, like I said before, at the end of the day, one of the main objectives of regression analysis is to make conclusions about the true relationship between independent variables and the dependent variables. So we want to make some conclusion about the population parameters, which in this case are beta 0, beta 1, beta 2, the coefficient, the population coefficient of independent variables in the regression equation, right? So we want to make a general conclusion about those. And the statistical procedure for that is called statistical inference. The process is called a statistical inference. We're already familiar with the process. In this video, I'd like to focus on the necessary conditions for residuals. So in order for the regression model to be an accurate regression model, we need to have some conditions for the residuals. We need to check these conditions every time that we are running a regression analysis, right? So what are these conditions? Very simple. The error term epsilon, which we estimate error term using the residual, right? That should be normally distributed with a mean of 0 and a constant variance. A constant variance, mean of 0, and normally distributed. So this term by itself actually is depicting 3 conditions for error terms. So it should be symmetrical, it should have a mean of 0, and it should have a constant variance. So 3 conditions, and then we have a 4th condition, which says the values of error terms, the residuals, should be statistically independent. There shouldn't be any relationship between them. If you know one of them, you should not be able to guess the next one. So that's the meaning of it. So they should be completely random, right? So this is an example of what we are talking about. They should be at each range, at each small range, at each range of x, the distribution of error terms, if you just take the regression and find the residual at each neighborhood, at each small neighborhood, at each point, you should get a normal distribution with the mean of 0 and a constant variance. As you can see, the distributions, they have constant variance. They should have constant variance in order for us to be able to generalize the result that we get from the regression model. So when we have, how do we test that? Using the residual plots in Excel. So we're gonna do that when we are dealing with numerical examples. But here I want to focus on the concept here. So this is a good example of the residual plot. So the residual plots, it's a scatter chart that shows residuals, right, EIs, with respect to X or Y hat. The independent variable or estimated value for Y doesn't really matter. This doesn't change anything, right? So what matters is the residual should be on the vertical axis. And I said we should have a normal distribution at each small neighborhood. That means we should have approximately equal number of points above and below 0, symmetrically distributed, all right? And which means that on average, the distance should be more or less the same from 0. Right? Mean should be 0, which means that at each neighborhood, at each small neighborhood that you take, the center of the points that you take should be 0. Variance should be constant. As you move from left to right in this scatter chart, the variation between points should be more or less constant. You shouldn't see a change in variance, significant change in variance as you move from left to right, all right, as you increase x or y hat. So this is a good example. This, if you see a residual plot like this, you should say this, I mean, there is no violation of the necessary conditions for residuals, so we can move ahead and make the statistical inference about the population parameters, about the coefficients of population line, basically. So this is a good example, and now I have a few bad examples. So here we have 4 examples. In each one of these examples, in each one of these panels, one of the necessary conditions is violated. So it's probably better if you guys just pause the video and guess it for yourself, like which condition is violated in each panel. So in panel A, as you can see, the center of the distribution is always 0 as you move from left to right. If you focus on a small neighborhood, if you take just the points that are like in a small neighborhood for x, you will have the center always as 0. So mean of error is always 0. So that's not violated. And always at any point, again, at any small neighborhood that you take, you will have almost equal numbers of points above and below the line. So that means you have a symmetrical distribution around 0, always at any small neighborhood. I'm not looking at the whole thing at once. I need to focus on small neighborhoods. Right? Which means that I just pick a number and then go a little bit to the left, a little bit to the right, and just focus on the points around it. So if I take, let's say, this neighborhood, I will have approximately equal numbers above and equal numbers below. The center is 0, so it's symmetrical. And then using the residual plots that we get in Excel, we can't really test the independence condition. So I'm just going to skip that. The only thing that is left is the constant variance. The variance is not constant as we move from left to right. You see here, the variance is almost 0. Points are all, like errors are all almost 0. And as I move to the right side, the variance in error increases. All right, so the variance becomes significantly larger than 0 compared to here. All right, so variance is increasing. So that's a violation. So panel A doesn't show a constant variance as we move from left to right. In panel B, what is the violation? I have, again, if I focus on a small neighborhood, I have at the center of the points, I have approximately equal numbers above, approximately equal number of points below. So it's symmetrical around its center. But the problem here is that the center is not anymore in 0 like we had before. So here the center of the point, if I focus only on points around, let's say 0, most points are above 0. So this mean of error here is not 0, is a positive number. And if I take a small neighborhood here at the center, at the middle points here, And if I take the average, if I take the mean is a negative number. And if I go to the right side of the distribution and take a small neighborhood, the average error here is positive. So positive, negative, positive. It's not always consistently equal to zero. So that's a violation. Mean of error is not always equal to zero for all values of X. So that's a violation. Panel C, mean of error is zero, always, right? So if at any neighborhood that you take, you have, if you take the mean average error, approximately speaking, you will have always a mean error of zero. Variance is also constant as you go from left to right. You don't see like this one, you don't see significant change in variance. And you can actually measure the variance. I mean, this is a really subjective judgment. It's based on our observation. We don't really quantify it. When you're just looking at it, you can use the range of observation. So the range of observation from here to here is almost the same. So the distance between the smallest number and the largest number here would be the range. Here versus here versus here, the range is more or less the same. So that can be your proxy for checking the constant variance. So mean is zero, variance is constant. What is left that is not satisfied? The symmetry assumption. It's not symmetrical around zero. So we have a lot of points below zero, but very close to zero. And we have very few points above zero at the positive side, but very far from zero. The center is still at zero, but I don't have equal number of points below and above, which is the condition for symmetric assumption, basically being symmetrical, the distribution. So I don't have that condition, so that violates my necessary condition. The last panel, it's just notice that this is with respect to t, not x anymore. So in order to be able to check the independence condition, we need to have a graph that is with respect to the order of selection. So this now is residual with respect to the time or the order of selection of that specific data point. If you see here, there is this very specific pattern when we draw it based on the order of selection. So I have negative error, then positive, positive, negative, negative, positive, positive, negative, negative, positive, positive. So always two negatives, two positive, two negative, two positive. Almost. I mean, sometimes it's not 100% accurate, but if I know an error, with a very good chance I can predict what the next error, or at least the sign of it, would be. So if this is negative and I have just one negative here, I expect the other error to be negative based on my previous actually experience from the data, right? So this shows that these data points are not picked, are not selected randomly. There is a relationship between, there is a systematic relationship between the errors here. So that violates the independence condition for residual. The next graph, again, this is a good example. It's for Butler Trucking Company, multiple regression. So in this example, again, this is a very good one. So the center of error is at zero. We'll see constant variance as you go from left to right. You see the range is almost the same. So constant variance, and it's symmetrical always at any small neighborhood. When I'm talking about small neighborhood, you can just focus on each one of these bars here. All right, so for each bar, you have approximately equal number of points above and below. So that satisfies the symmetry condition. And then, like I said, given the residual plots in Excel, we won't be able to check the independence condition because we don't have the order by which the data points have been selected, have been picked. All right. So this is what we can actually check. So just to summarize, there should be 4 conditions for residuals: symmetry assumption, symmetry condition, mean of 0 always at the whole range of X, and then constant variance again at the entire range of X. And then the last condition, which we are not able to test in Excel, will be the independence check. So you just need to have, I just have this graph, you just have to have the graph of scatter chart of residual with respect to the time of selection or with respect to the order of selection. And if you see a pattern, that violates the um, randomness condition, independence condition between error